This presentation discusses about the descriptive inorganic chemistry of hydrogen and hydrides. Robert Boyle, 1627–1691, the father of chemistry, produced a paper in 1671 in which he represents the reaction between diluted acids and iron filings that result to the evolution of gaseous hydrogen. Although it was recognized sometime later as an element by Henry Cavendish, 1731–1810, in 1766, he is an English chemist and physicist, who also discovered the element nitrogen. He described this element as inflammable air from metals. He also observed its properties and thought mistakenly that the gas originated from the metal rather than from the acid. In 1783, Antoine Lavoisier named it hydrogen. In 1931, Harold Urey, a professor of chemistry at California and Chicago, USA, discovered deuterium gas, 2H2, often written D2. It is a heavy isotope of hydrogen which contains one proton and neutron, and the neutron in the nucleus. Physical properties of hydrogen. Colorless. Phase changes from a gas to a liquid at a temperature of -252.77 degrees C, -422.99 degrees F. Changes from a liquid to a solid at a temperature of -259.2 degrees C, -434.6 degrees F. Odorless. Tasteless. Density the lowest of any chemical element, 0.08999 grams per liter, the least dense of all gases. Solubility slightly soluble in water, alcohol and some other common liquids. Chemical properties of hydrogen. What are the chemical properties of hydrogen? Chemical formula H. Hydrogen gas, H2. Oxidation: it burns in air or oxygen to produce water. H2 reacts with every oxidizing element. Reactivity with gases combining hydrogen and nitrogen at high pressure and temperature produces ammonia, New Hampshire 3. Combined with carbon monoxide produces methanol, CH3O. Reactivity with nonmetals: it combines readily with nonmetals, such as sulfur and phosphorus. It combines readily with the halogens which include fluorine, chlorine, bromine, iodine, and astatine. Flammability: highly flammable, a highly combustible diatomic gas. Combustion: when mixed with air and with chlorine it can spontaneously explode by spark, heat or sunlight. Example, the destruction of the Hindenburg airship. Acid compounds. Common acids include hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, NO3, acetic acid, HC2H3O2, and phosphoric acid, H3PO4. Hydrogen is a unique element. It does not belong to any other groups in periodic table of elements. Some put hydrogen as a member of alkali metals, or on the halogens, others on both locations. But few place it on its own. In Table 1.1, the basic reasons for and or against placement of hydrogen in either group I or group 17. Hydrogen has higher electronegativity, tendency of an atom to attract electron, than other alkali metals and lower than those to the halogens. Therefore, it should be placed between the two groups. Hydrogen gas, H2, solidifies at 22,598 degrees C and liquefies at temperature at 22,538 degrees C. It is not reactive because of hydrogen-hydrogen, HH, and covalent bond energy at 436 kJ/mol1. Moreover, the hydrogen does not react with dioxygen. If H2 and O2 are mixed, the reaction may be explosive. Also, when a dihydrogen reacts with halogens, F, Cl, branch, I, and it, with decreasing rate of reaction, it has a violent reaction. Dihydrogen and nitrogen reaction is very slow in the absence of catalyst. Dehydrogen reduces metal oxides to a metallic element at high temperatures. Hence, copper, oxide is reduced to copper metal. Henry Cavendish, in his report to the Royal Society of London in 1766, described the properties of hydrogen gas. He showed that hydrogen is lighter than the air. When hydrogen, water producer, and oxygen, acid producer, reacted together, it produced water, H2O. When metals like iron, Fe, or zinc, Zn, react with a strong acid such as sulfuric acid, H2SO4, or hydrochloric acid, HCl, it produces hydrogen in the laboratory. See equation 1.5. Moreover, it is common to reverse the reaction between oxygen and hydrogen by carrying out electrolysis of water, as equation 1.6 shown. Some uses of hydrogen can be a clean fuel, hydrogen-powered fuel cells, for the future. It will be generated from water and returning to water when it will be oxidized. It is a pollution-free source of energy. In chemical industry, it is used to make ammonia, New Hampshire 3, for fertilizer and agriculture. For instance, Haber process is an industrial process for producing ammonia from nitrogen and hydrogen, using an iron catalyst at high temperature and pressure. Furthermore, it is used for the production of pharmaceuticals and plastics. Besides, it can remove sulfur from fuels during oil refining process. In addition, it is used to hydrogenate oils to form lipids/fats, for example, margarine. Hydrogen is very flammable whenever it mixed with pure oxygen. So, it is used as a fuel in rockets. Normally, liquid hydrogen is combined to the liquid oxygen for an explosive mixture. But unfortunately, U.S. Space Shuttle Challenger exploded in 1986 when a flame ignited the liquid hydrogen in external fuel tank. It is a lesson that this gas is so dangerous and can cause disaster in any cases. Hydrogen has 3 isotopes: protium, H, or common hydrogen, which contains 0 neutrons, abundance 99.985%, deuterium, D, which contains 1 neutron, abundance 0.015%, and radioactive tritium, T, which contains 2 neutrons, abundance 10,215%. As the molar mass of these isotopes increases, boiling point and bond energy also increase significantly. See Table 1.2. Deuterium, D, and tritium, T, covalent bonds are stronger than the common hydrogen. For instance, when water is electrolyzed to give hydrogen gas and oxygen gas, it is the OH covalent bonds that are broken more readily than OD bonds. As a result, the remaining liquid contains a higher and higher proportion of heavy water, deuterium oxide. Tritium, T, has half-life of 12 years. It is formed on the upper atmosphere by the impact of cosmic rays on atoms. Its output involves the impact of a neutron on a nitrogen atom. The isotope decays to give the rare isotope of helium, helium-3. Tritium, T, is very useful as a tracer in medical purposes. It emits low-energy electrons because of its radioactive decay. Moreover, in military forces, tritium, T, occur in synthetic route, which involves the bombardment of Li-6 by neutrons in nuclear reactor. Hydride is the anion of hydrogen, H, or, more commonly, it is a compound in which one or more hydrogen centers have nucleophilic, reducing, or basic properties. In compounds that are regarded as hydrides, hydrogen is bonded to a more electropositive element or group. Compounds containing hydrogen bonded to metals or metalloid may also be referred to as hydrides, even though in this case the hydrogen centers can have aprotic character. Periodic table of elemental hydride types. These substances have been classified into 3 main types according to the nature of their bonding: ionic hydrides, which have significant ionic bonding character; covalent hydrides, which include the hydrocarbons and many other compounds which covalently bond to hydrogen atoms; metallic or interstitial hydrides which may be described as having metallic bonding. Intermediate hydrides composed of polymeric and borderline hydrides. Elements of group I and II except B in milligrams form ionic hydrides. In these hydrides, bond between metal atom and hydrogen atom is ionic. Ionic hydrides are also known as saline hydrides or salt-like hydrides because their properties are identical to salts. Ionic or saline hydride is a hydrogen atom bound to an extremely electropositive metal, generally an alkali metal or alkaline earth metal. For the hydrides of group I, MH, where M represents Li, N, K, R, B, CS and Fs. Examples, Li, No, KH, RBH. For the hydrides of group II, MH2, where M represents Ka, Senior and Ba. Examples, Ka2, SRH2, Ba2. Ionic hydrides can be prepared directly on passing hydrogen gas over hot alkali metals or alkaline earth metals. General expression of preparation. Ionic hydrides are solids. Thermally very stable. Have high melting and boiling point. Soluble in water. Insoluble inorganic compounds. Conductors, electrolytes, of electricity. Elements of group 3 to 7 form covalent hydrides. They possess covalent bond in their structure. For example, BH3, Al3, CH4, New Hampshire 3, H2S, HCl. Covalent hydrides cover all other compounds containing hydrogen. Some definitions limit hydrides to hydrogen centers that formally react as hydrides, that is are nucleophilic, and hydrogen atoms bound to metal centers. Covalent hydrides can be prepared by two methods: the direct method, an indirect method. 1. Covalent hydrides are gases or liquids. For example, gases, CH4, New Hampshire 3, H2S. Liquid, H2O, HCl. 2. Liquids are volatile. 3. They have low melting and boiling points. 4. They are colorless compounds. These are the hydrides of transition elements, except elements of group IB and 2B. In transition elements there are small empty spaces among the atoms. Hydrogen gas adsorbs in these empty spaces to produce non-stoichiometric hydrides or interstitial hydrides which are known as metallic hydrides. 1. They do not follow stoichiometric rules. 2. They behave like pure metal. 3. Bonding between metal and hydrogen is metallic bond. 4. On heating they release hydrogen in atomic state. 5. They are solids. 6. There is no true chemical reaction between metal and hydrogen in these hydrides. 7. They are not true chemical compounds. 8. They are used as reducing agent in different processes. Polymeric hydrides. Hydrides of beryllium and magnesium are known as polymeric hydrides. In polymeric hydrides a large number of Be2, or MgH2, units are joined together by hydrogen bonding to produce long chain of Be2, or MgH2. General representation: Be2, N, MgH2, N. Borderline hydrides. Hydrides of the elements of IB and 2B and, in, indium and thallium, Tl, are known as borderline hydrides. Examples: Q2, ZnH2, TlH2. 1. Borderline hydrides exhibit bonding characteristics between ionic and covalent bond types. Q. Copper hydride, that appears as a spongy reddish-brown substance, is a moderate reducing agent. It will catalytically oxidize hypophosphorus acid to phosphorus acid at room temperature, and it gives off hydrogen gas when subjected to heat. 2. ZnH2 is also a solid at room temperature that breaks down at 90 degrees C, but even left alone decomposes over several days to zinc metal and hydrogen gas. Here are the applications of hydrides.